me. So we're going to continue our discussion from this portion, and we are still on convection. Okay, last week we looked at the thermal boundary layer, velocity boundary layer, and then we look at certain basic definition in relation with heat transfer, such as Nusselt number, Prandtl number, Reynolds number, and we look at laminar flow and turbulent flow condition. Okay, so basically, all the equations that we have derived, we will try to use them in solving questions later on. But today, our discussion is going to focus on force convection across a cylinder. So last week, we looked at force convection across flat surfaces, or let's say horizontal flat surfaces. Okay, but today, we're going to look at the nature of force convection across a cylindrical object or even spherical object. Okay, so similar correlations applied with regards to force convection across flat surfaces. Okay, so we have noted that for a cylinder, okay, or even for a horizontal surface, or let's say we have a flat plate, the basic equation for fluid flowing across a flat plate, the Nusselt number is governed by HL divided by K, where H is the heat transfer coefficient, L is the characteristic length, and K is the thermal conductivity. And based on the nature of the flow, if the flow is laminar or the flow is turbulent across the flat plate, then the appropriate Nusselt number equation is always a function of Prandtl number and Reynolds number. You understand me? So the same situation is for a cylinder. For a cylinder, the difference over here is that this L is going to be changed to D. You understand? So here we have the general equation for the definition for Nusselt number for a cylinder is given by HD divided by K. Okay? And for a cylindrical surface, for fluid flowing across a cylinder, this is the governing equation. Okay? So it's an empirical equation. So empirical equation means that somebody who has conducted an experiment, okay, and they observed that the Nusselt number across a cylinder is a function of both Prandtl number and Reynolds number, and it is governed by this equation. You understand me? So if you are asked to calculate, let's say, the heat transfer across a cylindrical surface, the first thing is that we need to use this particular equation to determine the Nusselt number. So it means we need to use this particular equation to determine the Nusselt number, and then it means we need to find the Reynolds number, the Prandtl number. We substitute into this equation, and that gives us the value for Nu. Then consequently, we have to find the value for H, given that we have Nu already. Okay? So Whittaker developed this empirical equation for flow over a sphere. So if you are using a spherical surface, the governing equation or empirical equation is this equation. Okay, so you see, again, this is the diameter of the sphere. For a cylinder, this is the diameter of the cylinder in this way. So various governing equations are being given over here. For a circle, if you have fluid flowing across a circle, and then you discover that the Reynolds number of that fluid falls between 0.1, 0.4, and 4, then you are advised to use this Nusselt number. Okay, so you use this value to determine the Nusselt number. I've told you Nusselt number these are empirical equations. Okay, these are equations developed from experimental values. So when you get this value of Nu, then if you want to find the value for H, then you use this general equation. Is applicable to all spheres or even cylinder. So H D divided by K. So when you calculate the value for Nu, you substitute into this equation, and then important thing is that we want to calculate the value for H. So H will be equal to Nu, okay, times K divided by D. So D is known already, thermal conductivity is known already, so then you can find the value for K. And then eventually we can use this to determine the convection heat transfer, which is H A delta T. You understand? Okay, so now for a square also, okay, if you have fluid, especially for a gas flowing across a square, then again, if your Reynolds number happens to fall within this range, then there's a Nusselt number to use. So again, this is a square tilted at a certain angle, 45. We have hexagon, we have hexagon tilt, and then vertical plate, ellipse. All these are the empirical equations for these geometries. Okay, so we will come back to this particular question in the end of the slide. Okay, so let us consider this question first. Here we are told that a long diameter hexagonal steam pipe. So it means steam, let's say, is flowing into this particular pipe, whose external surface temperature. So the surface temperature is given 110 degrees Celsius, passes through some open area that is not protected against the wind. So the hexagon tube happens to pass through, let's say, air whose properties are velocity is 8 meters per second, temperature is 10 degrees Celsius. So definitely, obviously, there will be interaction between the atmospheric air and then the surface of the hexagon. You understand? Because this is a hot surface, there is bound to, for the heat to be transferred from the outer surface of the hexagon to the air. And the mode of heat transfer is Q, convection. You understand? So we are to determine the rate of heat loss. So it means we have to find Q, H, or Q equals to, that's the convection heat transfer, equals to HA times what? Delta T. This is the whole thing. You understand? So here what we need to know is that the value for delta T is the difference between these two temperatures, Ts and T infinity. And the area, we need to determine the surface, the total surface area of the hexagon. So namely, we need to find this surface area first. You see, if you know the surface area, then we will multiply by 6 because the total surface area for the hexagon is 6. We have 1, 2, 3, 4, 5, 6. These are the total surface area. So if you're able to calculate one side, then you just multiply by 6. You understand me? So it means we are now, the challenge is that we need to find this particular width. And then if the length is given, the area will be length times breadth. You understand? So like this. So yes, so now we need to know the appropriate governing equation for the fluid flowing across the hexagon. Okay, this will help us to determine the Nusselt number, which is a function of PR and RE. Okay, so also we need to determine, since we are known that Nu equals to K, Nu equals to HL, HD, divided by K. How do we determine the value for K? So all these thermal properties, density, thermal conductivity, Prandtl number, okay, kinematic viscosity, all this can be determined by finding what we call T film. And T film is the average temperature of the hot plate and then the air. So at that particular temperature, you are going to read from the table the density of the fluid, thermal conductivity, PR, and kinematic viscosity. Okay, so you have to be very careful in estimating this film. Even max is awarded to this thing also. So now we have 60 degrees Celsius. So we now go to table A15. From this table, we can determine all the thermophysical properties for the air, which is thermal conductivity is this. We have kinematic viscosity and Prandtl number. Okay, so now we determine, yes, the Reynolds number also. What is the nature of the flow? Is the flow laminar flow or is the flow turbulent flow? Okay, so, and also, and I have told you, Nusselt number for hexagon. You see, the Nusselt number can be determined from table 7.1. In your textbook, if you look into your textbook, table 7.1, at this particular Reynolds number. So the Reynolds number is given by V, that's the velocity of the fluid, hydraulic diameter, and then the kinematic viscosity. And then our Reynolds number is given by this. So now, based on this Reynolds number, we need to find the appropriate Nusselt number. Okay? So now, we discover that in this particular table, the appropriate Nusselt number is given by this equation. Okay? So now, we know the Prandtl number, we know the Reynolds number, we substitute into the equation, then we get the value for NU. So now, we have to use this NU equals to HD divided by K to find the value for H. So, and that is it. So H equals to 34.4 watt per meter square per degree. Okay? So now we need to find the area, the total surface area of the hexagon. Now, be careful over here. We have taken only the side view of the hexagon. Okay, forgetting about the surface. So if this is the surface, okay, this is one surface of the hexagon. Okay, so we need to find, if we are able to find the surface area of one side, okay, we find, for example, this surface area, then we multiply by 6 because we have 1, 2, 3, 4, 5, 6 surfaces. You understand? So now, how do we determine this surface? Let me show you. Okay, so if we let the diameter of the hexagon be D, diameter equals to D. So this is the diameter, is equals to D. So it means half of this diameter, half of it is going to be D divided by 2. Okay, so then with this becomes, and then the angle subtended by this particular line, okay, is given by 60 degrees. So if we take only the half portion, so it's going to have, we will have something like a rectangle triangle, like this, okay? And then we have the angle to be 60 degrees. So we know this height to be d divided by 2. So we are interested in this hypotenuse. So we represent it by x. So now sine 60 gives us opposite over hypotenuse. So we have d divided by 2 all over x. So what is x? X equals to d divided by 2 times divided by sine 60. Okay, so now we have been able to find this side. Now we know the length. Length is given to us already. The length is, assuming the length is L. So it means the whole surface area, one surface area is going to give us x times L. So that gives me d divided by 2 all over sine 60 degrees, sine 60 degrees, sine 60 degree times L. Okay, so now, but we have this constitute for only one phase. So we need to multiply this by 6 in order to find the total surface area. So now this gives us this. Okay, so the final equation is this. So we multiply by 6 and then times this area. Okay, so that gives us the total surface area. So eventually we will have the area, the total cross-sectional area is given by this. Okay, total surface area, sorry, is given by 0.346 meters squared. Okay, so now we know the area, we know the value for H, we know delta T. Easily we can estimate the heat transfer, which is 1,191.7 watts. Okay, so now let us proceed to a very important area. So you see, in heat transfer, we have discovered that we are very much interested in the Nusselt number and then the skin friction coefficient. Okay, so these two parameters play a very important role in thermal engineering. Okay, because the coefficient of friction is normally used to calculate the shear stress. You understand? So, and then the Nusselt number is also used to calculate the heat transfer coefficient. You understand? So this is very, very important. Okay, I have told you that, so let's say if we have fluid flowing across a flat plate like this, the development of the boundary layer across the flat plate is this. At this point, the velocity equals to 0. So velocity will be changing gradually, 0, 2, 4, 5, 6, until when it reaches a point, okay, whose velocity equals to 99% of the free stream velocity, then that distance is given by the velocity boundary layer. Now, within this velocity boundary layer, there is always, because the velocity is changing, if you assume two fluids, okay, so two fluids, one, the velocity of this, let's say, equals to 2, the velocity of this, let's say, equals to 6, this will be moving very, very, very fast compared with this. So they will develop a certain shear force between the two fluids. There will be a relative shear force, and then which is given by this tau. And this tau is always a function of the skin friction, okay, the coefficient of friction. It's very, very, very important. As long as the velocity is changing in this region, then again the shear force also will be changing. And consequently, there will be a coefficient of friction that will exist between the fluid. Okay, so that is it for the for this particular CF. Now, if we look at the thermal or the Nusselt number, okay, so the Nusselt number by definition again, is given by HL divided by K. Okay, so this gives us the convection heat transfer, and this gives us the conduction heat transfer. So which one of them dominates when the fluid is flowing across the flat plate gives us idea about the heat transfer phenomena. You understand me? So as the nozzle normal is normally correlated with the heat transfer situation when the fluid is flowing across the flat plate, whereas the skin friction coefficient, again, is related to the skin friction coefficient. So these two parameters are very, very important when it comes to heat transfer analysis. So we are going to develop a relationship between this CF and nozzle normal so that when one is absent, then the other can be calculated in this way. So it is this scientist, so later the Stantoff, okay, who came out with the relationship between the two parameters. So he mentioned that, or the Cheltenham-Colburn analogy, okay, mentioned that the relationship between nozzle normal and skin friction coefficient is given by this particular equation. So skin friction coefficient as the Reynolds number of the fluid divided by 2. But this is subjected to the condition that the PR should be equal to 1. You understand me? So when PR equals to 1, then this equation is valid. On the other hand, so Stantoff also make a modification of this equation and then came out with this equation that the Stantoff number equals to CF divided by 2. Okay, so another development of the Stantoff number is given by this. So the Stantoff number equals to the heat transfer coefficient divided by Cp times the rho and then the velocity of the free stream. And again, this equals to Nu divided by Re times PR. Okay, so now you see, we are told over here that Reynolds analogy is important because it allows us to determine the heat transfer coefficient for fluids where the Prandtl number equals to 1. And from the knowledge of the skin friction coefficient, which is easier to measure. So it means if you measure the skin friction coefficient, easily you can determine the value for H using the Reynolds analogy. So now, what about, yes, so that situation, that condition is this. For Prandtl number equals to 1, and then you have the velocity boundary layer, okay, being developed within this region, okay, and then also velocity or thermal boundary layer, which is given by this line, okay. So, and the Reynolds analogy is normally applicable for situations, especially with Prandtl number being equal to 1. Okay, so now the same situation we have over here. Now, however, the Reynolds number is of limited use because of the restrictions. What is the restriction? Prandtl number equals to 1. There is no pressure gradient. Okay, the P over the X equals to 0. Okay, so the pressure does not change. It means that within this boundary layer, the pressure is assumed to be constant along the X direction. So pressure does not change. Okay, pressure gradient equals to 0. Therefore, it is desirable to have an analogy that is applicable over a wide range of Prandtl number. So this is done by adding a Prandtl number correction factor. So now, by doing this, the equation is modified a little bit. Okay, so this is how, if you recall, skin friction coefficient governing equation is this, and then nozzle number, also the governing equation is this. If you divide CF divided by Nu, then we are going to get this equation. We'll get this particular equation. Okay, so for example, over here, we have NU, let's say NU divided by CF equals to 0.332 PR 1/3, and then RE half, RE 1/2, all divided by 0.664, and then RE 1/2. So this goes into this, becomes 2. And then we have RE over here, RE over here. So this goes up. Then eventually we will have NU divided by CF equals to PR 1/3 times RE. Okay, so this is negative half. If it goes up, it becomes positive. So now negative half plus half is 1. Okay, so it leaves like this. So all divided by 2. Okay, so now eventually we will have CF divided by 2. Okay, so we will have CF divided by 2. This goes up, and then this comes down. So then we will have this should be equal to, this will be equal to, we'll have this comes, this goes upstairs. So then this comes down. So yes, we have NU divided by PR 1/3 and then RE. Okay, which is the same as this. The same as this equation. Okay, because this is negative, but this is positive over here. And then we have positive 1 over here, so negative 1. Now, this final equation is what we call the Coleman-J factor. Okay, so which is used to estimate the skin friction coefficient, okay, when the Nusselt number is known. You understand me? So PR and RE can also be equally determined. So another version of this equation can also be written in this form, okay, by making substitution for the NU, okay, relation. Then eventually the whole equation becomes this, okay, and then we have the RE also, they make a substitution for it. So final equation is this. So now, and the Chilton-Coleman analogy is derived using the laminar flow over a flat plate. Okay, so now we want to know, does it occurs also for a turbulent situation? So we are told that experimental studies, okay, have shown that it is also approximately applicable to turbulent flow over a surface in the presence of pressure gradient. You understand? So, the Chilton-Coleman analogy normally is applicable to laminar flow situation where there is no pressure gradient. Okay, but experimental studies have proved also that this analogy can be applicable to turbulent flow condition and with pressure gradient. Pressure gradient means we have the P over the X not being equal to 0. Okay, so like this. Now for laminar flow, it is not applicable unless it is a flat plate. Yes. So then therefore it cannot be applied to laminar flow in a pipe. You understand me? Also, the analogy above can be used for local or average quantities. Okay, so let us look quickly at this particular question. Here we are told that laminar flow profile over a vertical flat plate, okay, is we have the dimension of the flat plate is like this. We have the height is this. We have the width is also 2 meters plate. So this is a plate which is being suspended in the air. It's hanging in the air. So the air is flowing across both two surfaces. Surface number 1 and the opposite side also. Okay. So the plate is suspended in a room and subject to airflow parallel to its surface along its 3 meter side. Now, the total drag force acting on the plate. So when the air is flowing across the plate, there will be a force trying to drag the plate, and that total drag force is given by this. You understand me? So you see how important the skin friction coefficient now is playing a large role. Okay, so now determine the average heat transfer for the plate. Okay, so as usual, our T film is given by this. How do we determine this T film? T film is given by 25 plus what? 15 divided by 10. Oh, sorry, divided by 2. Very sorry. So that gives us 20, like this, 20 degrees. So it is this 20 degrees Celsius that we are going to use to determine the specific heat capacity for the fluid, the density of the fluid, Prandtl of the fluid. Okay, so the total area is the length times the breadth, and then times 2, because 2 surfaces. Okay, so now the equation for the drag friction coefficient or the drag force is given by this. Okay, half the skin friction coefficient. Okay, then we have the density of the fluid area, then the velocity of the fluid. So from here, we can determine CF equals to the whole of this. Okay, so D is the drag force. Okay, the drag force, which is the friction force, is given already in the question. Okay, so then divided by all these parameters, eventually you get a skin friction coefficient of this. So now we can use this to determine the heat transfer coefficient, which is also given by this. So we say from the modified Reynolds analogy, okay, the average heat transfer coefficient can be used. Okay, so now the heat transfer coefficient is this. Now we can use this equation to calculate HA times delta T. Delta T is the temperature difference, the area, and then we know the value for H in this way. Okay, so you know H already, you know the area, you know delta T. You can easily calculate the heat transfer coefficient. So quickly, let us move on to natural convection, and then we solve 1 or 2 questions, then we leave. So far we have completed forced convection. Now I want to look at natural or free convection. Okay, so in natural convection, you see, in natural convection, the fluid, or what is the difference between the two? In forced convection, if we have, let's say, a hot surface, the fluid is always forced to flow across the hot surface. Okay, so you have a blower that blows the air, okay, across the hot surface. So it means the fluid is forced to move in one direction. Whereas for free or natural convection, if this is the hot surface, okay, so the fluids move in different direction. Okay, so they move in different direction, and those fluids that are close to the hot surface will be moving upwards because of their decrease in density. You understand me? So the fluid will be moving in this direction. They are not forced to move in one direction. So they will be moving in different directions like this. So that's the classical differences. So now, to go a little bit into details, let's say we have a hot surface, vertical hot surface, okay, whose temperature is Ts. Now, assuming we have fluid layers that are directly or that are close to the fluid, sorry, the hot surface. These are fluids that are close to the hot surface. You understand? So what happens is that any fluid particle that is close to the hot surface, so let's say we have a fluid particle close to the hot surface, its density, so the fluid is going to expand because of the influence of the hot surface. The fluid will expand. When it expands, its density is going to drop. You understand me? So when the density drops, then immediately the fluid will be moving upwards in this way. So then again, those fluids that have high density, which are very far away from the hot plate, they will be moving down like this. They will be moving down. And then the low density fluid will be moving upwards like this. So we will have a situation like this where these are low density fluids. Now, because there is no any hot surface that continues in this region, then the fluid will be forced to move in this direction, to be diverting itself in this direction. So gradually, its temperature will become equal to the ambient temperature. So then again, its density is going to increase. So when the density increases, then again it will start dropping down. It will start dropping down. It will start dropping down. Then again, it will be approaching the hot surface like this. To be so the dense, because of the fact that you see, if this is a heavy molecule, heavy molecules, they will be forced to drop down. And then because the density of the fluid over here are very, 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 very low, then they will be forced to approach the plate again. So there will be a situation where there will be exchange in fluid conditions, and then there will be a natural phenomenon where the fluid will be flowing in this way. Okay, so this behavior or the change in density of the fluid is highly influenced by temperature. You understand me? So fluids with different temperatures will have different densities, and because of these different densities, the fluid will be moving upwards. And this movement of the fluid, because of the change in density, is what we call the buoyancy effect. Buoyancy effect. You understand? Okay, so this is the phenomena of natural or free convection. Now, let us see. We want to look at the thermal behavior of the fluid molecule, okay, in terms of natural convection. So we say in heat transfer, the primary variable is the temperature. So it is desirable to express the net buoyancy force in terms of temperature difference. Okay, so now what I mean by buoyancy force is that, you see, when the fluid is moving up, it's moving with a certain force, and this force is known as buoyancy force. So the force, it will be forcing itself to move up. Okay, it's not like this that there is a blower. There is no blower because of the difference in density. That's why the fluid is continuously moving upwards, and this phenomena is known as the buoyancy force. You understand? So now we have the buoyancy force in terms of the temperature. So the buoyancy force is directly connected to temperature difference. So this requires knowledge of property that represent the variation of the density of a fluid with temperature at constant pressure. So the volume expansivity or expansion coefficient, which is defined as a measure of the change in volume of a substance with temperature at constant pressure. This is the main parameter that influences the behavior of the fluid in natural convection. I've told you, any fluid that is in contact with a hot surface, the fluid will be expanding. And as the fluid expands, its density will be decreasing. So the density will decrease. Initially, the temperature increases, temperature of the fluid increases, and as the temperature increases, the density drops. And if the density decreases, then again, the volume, okay? So the volume, it means the volume will be increasing, volume expansion. So because of these situations, then you will have what we call buoyancy effect. So by definition, the volume expansivity is defined as the ratio of specific volume of the fluid times the rate of change of specific volume with respect to temperature at constant pressure. Okay, so this again can be represented in terms of density, because the fact is that what is definition for density? It is mass over volume. So 1 over density is the same as volume divided by mass. And volume divided by mass is what we call specific volume. I don't know, you have done this in thermodynamics, so this is specific volume. So from today, then you can know that 1 over rho is the same as specific volume. Okay? So it means that wherever we see, let's say over here, specific volume, we can be represented by density in this situation. So that over here, we will have, in place of the specific volume, we replace them by the density in this way. So that, again, yes, the negative sign indicates a decrease in density of the fluid. So as the temperature increases, the density decreases. Okay? So now, again, this equation can be rewritten in this form. So you see, this is delta, the rate of change of density with temperature. So we can represent it in terms of delta rho divided by delta T. So which is the same as this. And we can write it in terms of the differences. Okay? So here, rho infinity is referring to this fluid. So assuming this is the ambient condition. So rho infinity is referring to this, and T infinity, this is the ambient temperature. Now, the temperature of the fluid, which is close to the hot surface, is T, and its density is rho. Okay? So the difference between these densities, okay, is what we have over here. Yes, so is this. So it means this is the density for the ambient condition. This is the density close to the hot plate. Okay, so now the equation can be again expressed in this form. Rearrange, multiply the whole of this by this, and then we can write the equation in this form. Finally, again, we introduce a new, what do you call it? Parameter, sorry. And we using the ideal gas equation. So using the ideal gas equation, we know rho equals to P divided by RT. So ideal gas equation is given by PV equals to MRT. If I divide this by M, I divide this by M, this will cancel out. So we'll have P specific volume equals to RT. You understand? So it means that we will have, let's see over here, our 1 over specific volume equals to P divided by RT. Okay, so I'm taking this to this side, and then that one comes down. So this indicates that the rho, I've told you, 1 over specific volume 1 over specific volume is the same as rho. So we have density equals to P divided by R times T. So wherever we see, let's say, from the ideal gas equation, wherever we see density, okay, in this particular equation, we represent it by P, R, and then T. So here, the densities are represented by this equation. Okay, so eventually, we eliminate the derivative function, and then we discover that these parameters are the same as this parameter. So eventually you have 1 over T. Okay, so then we can, let's say the volume expansivity coefficient, beta, is always 1 over T. Now this temperature is always measured in Kelvin. The unit is always in Kelvin, not in degrees Celsius. You should be careful. Now, let us look at the development of the boundary layer. Okay, so we have known that the boundary layer for a flat plate, we have already seen the development of the boundary layer for a flat plate, for forced convection. Now, for a free convection, how is the development of the boundary layer? How does it look like? Okay, so now we have a vertical flat plate, okay, a hot surface, of course, and then we observe that at the exact surface of the hot surface, the fluid velocity is going to be 0. But as you progressively move towards the y direction, in this direction, the velocity of the fluid will be changing. So even though, yes, we can name this to be one fluid, this another fluid, this another fluid. The fluid that is here, its velocity equals to 0. And as you move along the y direction, the velocity will be increasing. Because of what? The influence of this the temperature of this surface will be expanding, will be increasing the volume of this fluid. So when the volume increases, the density will reduce, then the fluid will move up. Same thing applies to this, so then the fluid will move up. Same thing applies to this, but it goes on. Then as the fluid, as we move in the y direction, the influence of this temperature on the neighboring fluid will be reducing. So gradually, asymptotically, up to the free stream velocity. So then it becomes 0. You understand? So this is the velocity profile for the development of the velocity boundary layer in the in the free convection situation. Okay, so now this is the boundary layer. Now in this boundary layer, you see the velocity is changing, but outside the boundary layer, the velocity remains constant. If the velocity is 10, it remains 10. It does not change. You understand? So, but here again, the velocity is 0. So the fluid is not moving. It's stationary. Okay. Similarly, the temperature also across the flat plate, vertical plate, we have high temperature over here. So as you move in the y direction, temperature reduces gradually, asymptotically up to T infinity. So this is the velocity, the temperature profile with relation to natural convection for a flat plate. Okay, so now let us see. Now we know that in forced convection, we normally use Reynolds number to determine the flow situation, whether the flow is laminar flow or the flow is turbulent flow. It is the Reynolds number that will be able to tell you for a forced convection situation. So for forced convection, force convection. But for free convection or natural convection, we normally use what we call the Grashaft number to determine the flow situation. So Grashaft number is represent the ratio of the buoyancy force to the viscous force acting on the fluid. Okay, so Grashaft number provides the main criteria in determining whether the fluid flow is laminar or turbulent. For vertical plates, the critical Grashaft number is 10 raised to the power 9. Okay, so now this Grashaft number is governed by this equation. Grashaft number equals to gravity, gravitational acceleration constant, okay, of the fluid, volume expansivity coefficient, okay, then the temperature difference, and then we have the characteristic length divided by the kinematic viscosity. Okay, so this is the parameter which is used to determine the nature of the flow for a free convection. For a forced convection, we use Reynolds number. Okay, so here the Grashaft number is a measure of the relative magnitude of the buoyancy. I've told you, buoyancy force is the force which propels the fluid to move up because of its low density. But on the other hand, there is a friction because the fluid is directly held by the plate. There is a frictional force which opposes the movement of the fluid upwards. And this is given by the frictional force. So the ratio of these two gives us idea of the Grashaft number. So we say the Grashaft number is a measure of the relative magnitudes of the buoyancy force and then the opposing viscous force. Okay, so now there is one other equation called the Rayleigh number. The Rayleigh number is developed by this scientist, so it's just a modification of the Grashaft number. So Rayleigh number is equal to the Grashaft number times the Prandtl number. So then the equation can be given by this. And this is the Nusselt number for the plate. So basically, these are different geometries that are available depending on the flow situation. Okay, so these are empirical correlations, okay, with relation to average Nusselt number for natural convection. Okay, so for a vertical flat plate, the entire range of Rayleigh number, okay, we can use this Nusselt number depending on this range of Rayleigh number. Okay, so then for inclined plate, then the appropriate Rayleigh number can be used is this. For horizontal plate, also these are appropriate equations that are available. Yes, for a cylinder also, you see, this is a cylinder, horizontal, vertical cylinder. And then for a sphere, these are the appropriate Nusselt numbers. So now, and the first question which we saw before this, and let me see, where is it? Yes, there was one question which I told you we were going to discuss, but in any case, it is this one. Okay, here we are told that a 6-meter long section of 8-centimeter diameter horizontal hot water pipe passes through a large room. The pipe surface is 70 degrees Celsius. Determine the heat loss from the pipe by natural convection. So here, you are not supposed to find Reynolds number because Reynolds number will not give you any good information. First thing is to determine the Grashaft number. So if you find the Grashaft number, then based on this equation, then you are going to select the appropriate Nusselt number to determine NU. And if you find NU, then you equate it to NU equals to HD divided by K. So this is what you use to find the value for H. And if you get the value for H, then you can use to find H A times delta T, which is the convection heat transfer. That is all for both natural and forced convection situation. So quickly, let's move on. So our tail form is this. These are the thermal properties of the fluid. And then the volume expansivity coefficient is this. So you see it is in Kelvin. Be very careful over here. So the volume expansivity, expansion coefficient is always expressed in Kelvin. If you make a mistake and you write only 1 divided by 45, then again the whole thing will be wrong. Now the characteristic length is given. So now the Rayleigh number is this. So based on this Rayleigh number, we are going to select. So for a cylinder, you see this is horizontal cylinder. So our Rayleigh number is about 1.86 times 10 raised to the power 6. Okay, so which is a value which is less than this. So means that it is less than or equal to this. So it satisfies this condition. Hence, we can use this equation to determine the Nusselt number. So then that is it over here. Yes, so is it. Okay, so we use this to determine the Nusselt number. So Nusselt number is given by 17.4. So now based on this, we will use to determine the value for H. And consequently, we know the area pi dl, then we can find the heat transfer coefficient, which is this. So this brings us to the end of this particular chapter. Okay, so I will discuss one or two questions, and then we will stop, and later on we will start with chapter 4. Okay, so I'm trying to develop some quiz for chapter 1, 2, and 3. I'll post it on Google Classroom, and then you eventually have to provide a solution. Okay, so maybe it will be available by next week, early next week. Okay, so I'm prepared. I'll be solving one or two questions now, so that we will try to learn or discuss some of the things that we have learned today. Okay. So I'll start immediately so that we can save some time. We can finish quickly. Okay. Let me upload the question. So let me upload the question. Yes, so let me upload it now. Sorry, man. Yes, so now I have successfully uploaded the question. Okay, so quickly let us discuss. Okay, so a few minutes to take us. So if you look at question number 3A. So question number 3A says, by using, by using an example, describe the mechanisms of natural convection. Okay, so normally we can just describe that. Let's say we have a hot surface over here, mechanisms of natural convection. Okay, so like I've told you, we have high density fluid with low density, okay, moves up because of their increase in temperature. And then they move along this direction. Eventually they move down like this. Okay. These are high density fluid, high density fluids move downwards. And then low density fluids. These are low density fluids. Low density fluids move up. Okay. And we can say due to increase in temperature, increase in temperature, and increase due to increase in temperature and increase in volume. Increase in volume. Okay, so now we can say when a hot solid surface is exposed to the surrounding, so clearly we can say when a hot surface is exposed to the surrounding or to the surrounding, into bracket maybe cold air. Okay, the fluid adjacent to the solid. So let me move this up. The fluid adjacent to the solid surface will be heated. Adjacent to the solid, adjacent to the solid surface will be heated. Okay, and then expands. And expands. Okay, the buoyancy force created by the changes So buoyancy force, the buoyancy force created by the buoyancy force created by the changes in density of the fluid, by the changes in density of the fluid. Changes in density of the fluid will move up in the warm air, will move up the warm air or fluid, the warm fluid. And then the vacant space is replaced by cold fluid. And the empty space is replaced by cooler fluid. So the motion of this fluid that results from continual replacement of the heat fluids by the cold fluid is called natural convection. So eventually we say that the motion, the continuous motion of the fluids, okay, the continuous motion of the fluids, okay, of the fluids due to differences in densities, okay, result in buoyancy effect, and this is known as natural convection. Okay, so quickly, let us move on to the next question. So the next question we are told like this. I hope everybody can see. Let me make it a bit big. So I'm coming in. Okay, so according to this question, we are told that a thin metal plate. Okay, so a thin metal plate of dimension 0.5 meters by 0.5 meters is again fully insulated on the back surface. Okay, so we have, let's say, this is the metal plate. Okay, one side is insulated. Let's say the back surface is insulated. And then on the back surface. So while the front surface is maintained, so the surface temperature Ts equals to 70 degrees Celsius. If the plate is exposed to air at, so means T infinity equals to 20 degrees Celsius. determine the rate of heat transfer or the rate of heat loss from the plate by natural convection. So there will be heat loss from the plate by convection, and this convection is natural convection. So we need to determine this. So since I've told you this is a natural convection situation, so you see, we need to determine the Rayleigh number. So if you go straight away, you want to determine Reynolds number, then again the whole thing is zero, because Reynolds number is not going to play any major role in this situation. Reynolds number is meant for forced convection, and Rayleigh number is meant for what do you call it? Natural convection. So first thing that has to come to our mind is that we need to determine the Rayleigh number. Okay, so a range of Rayleigh number has been given to us in the table. If you look at table below, okay, we have Rayleigh number 10 raised to the power 4 up to 10 raised to the power 9 or so. Yes, so then that appropriate Rayleigh number is this. For this situation, the appropriate Rayleigh number is also given by this. Okay, so we need to also, because of the fact that the Rayleigh number equation, you see, is given by Rayleigh number equals to G. So all this equation will be given to you in final exams. So no need to memorize it. So Ts minus T infinity, okay, L raised to the power 3, characteristic length, divided by kinematic viscosity square. Okay, so we need to find, so the gravity is always a constant, is always given. Now we need to find B. How do we determine this? Beta. Beta is the volume expansivity coefficient. So the volume expansivity coefficient is given by 1 over T. Okay, so 1 over T. So that gives us the average temperature. Okay, so we will find the film temperature. Film temperature, T film equals to the temperature of the fluid, which is 20, okay, plus temperature of the hot surface, 70, all divided by 2. So this gives me 45 degrees Celsius, 45 degrees Celsius. So it is this 45 degrees Celsius we will use to calculate the beta. So beta equals to 1 over, be careful, 45 plus 273. So if you calculate this carefully, then that gives us 0.003145, okay, Kelvin. So we have Kelvin. You understand? So this is how to calculate. Now we are going to use this 45 degrees Celsius to determine the appropriate, the thermal properties of the fluid. You see, the thermal properties of the fluid is given in the table below. Okay, we have the at 20 degrees Celsius, density is given, thermal conductivity is given, again, dynamic viscosity, kinematic viscosity, Prandtl number, and so on and so forth. So if you don't calculate this T form very well, then again, the whole thing is going to be wrong. Okay, so appropriately, we are going to use the values for 45 degrees Celsius. You understand? So now, as far as the Grashof number is concerned, the Rayleigh number is concerned, we have Ra equals to gravity, we know, equals to 9.8, okay, 9.81 times 10 raised to the power, 10 raised to the power, times 0. Times the beta, so I have this value, 0.003145 Kelvin. Okay, then times the temperature, difference. So that gives us 70 minus 20. Okay, so then we have the length also. Okay, so the length raised to the power 3. So the length of the plate is given, let's see what is the length. So L is given to be 0.5. So L equals to 0.5. So we have, L equals to 0.5. So we have 0.5 over here, raised to the power 3, all divided by, so the kinematic viscosity. So what is our kinematic viscosity is given here? Our kinematic viscosity is 1.7. So that gives us 1.75, 1.75. Okay, so 0 times 10 raised to the power minus 5 square. Okay, so if you calculate this carefully, oh yes, so let's see, times the Prandtl number. We are forgetting we didn't multiply by Prandtl number. Prandtl number is 0.72. So in this equation, there is Prandtl number. Very sorry. So we have PR over here. So Prandtl number is there. Okay, so we should multiply by the Prandtl number. So that gives us 0.724. Okay, so then if you calculate this carefully, we'll have 4.559 times 10 raised to the power 8. So now, with this Rayleigh number, we will go to the table. So let's see, we have 4.5 times 10 raised to the power 8. So now, if you check carefully, we have over here 10 raised to the power 4, and then 10 raised to the power 9. So the first equation is going to be the appropriate one to use. 0.59, okay, times the Rayleigh number 1/4. Okay, so clearly like this. So we will use, it means NU. We are going to use this NU equals to 0.59 times Rayleigh number 1/4. Okay, this gives me 0.59 times 4.559 times 10 raised to the power 8, all raised to the power 1/4. So you calculate this carefully. Then again, you get 86. So this is a dimensionless parameter. Okay, so now we're going to use this to determine the value for H. So we know that by definition, NU, this is the general equation for NU. NU equals to H. Now, this is a flat plate, so we should not use D. Instead, it should be L divided by thermal conductivity. So my H equals to NU times K divided by L. So now eventually this gives me, if you follow this carefully, we know the value for NU, we know the value for K, we know the value for, again, you are going to select the K at 45 degrees Celsius. So where is our K? Thermal conductivity, yes, this one, thermal conductivity. So 0.02699, that's the value for our thermal conductivity. So Nusselt number is given already. So we have 86.211 times 0.2699, all divided by the characteristics length. Okay, so now this gives us 0.5. So eventually we will have H equals to 4.60 watt per meter square per degree Celsius. So finally, Q, that's the heat transfer, equals to HA delta T. So H is given already. So this is the value for H. H is equals to that. Okay, so now 4.60 times the area. Area gives us, we have 0.5 times 0.5. So 0.25. So that gives us 0.5 times 0.5. Okay, so then that gives us times the temperature difference. Okay, so temperature difference gives me 70 minus 20. Okay, so eventually, let me see here, the dimension of the system is, let's say, 0.5 millimeters, okay, by 0.5. Yes, that is correct. Okay, so now we will get 0.25, okay, for the area. So eventually the whole thing becomes 57.5 watts. So this is the final answer. So it's a very simple case of convection heat transfer. Okay, so we will stop over here. Next time we will look at question number 2, and then maybe question number 1. That's for the conduction part. Okay, so and let me hear from you if there is any question, anything bothering your mind, any discussion, even anything outside this particular class, how you want the online discussion to be done, okay, from your point of view. Then if you discover any weakness, so in the lecturing, then again, you should tell. Okay, so then in this way, we can all discuss. Okay, so I would like to stop over here. Is there any question so far? If there is any question, please let me hear. Otherwise, if there's no question, then I think we will stop over here. And then we will have our short discussion. Okay, so far, there is no question from anybody. Okay, so I will end the presentation over here.